Welcome back to the Thermofluids book club. And we're now going to get back in the world of thermodynamics. And honestly, because we did all the work in statistical mechanics, sort of chapters 5 and 6 here that deal with entropy is going to be a lot more natural to deal with. Okay? And so really the first thing that we need to talk about in this section again is reversible. So reversible process versus irreversible. Okay, reversible basically means that the ds is 0, right? That you didn't generate any entropy, and really this is dq is equal to 0, right? If remember, the whole heat is related to the entropy generation. So that's what we're talking about. So reversible things are going to be things like friction would make things irreversible. Why? Because there is some heat, right? So dq is greater than 0, and so you're going to have a change in entropy. It's going to make things different. And so what's nice now is with the tools behind us within entropy, we can actually start looking at cycles, and that's really like the point of thermodynamics is you can actually do the calculations and talk about engines, like combustion engines, jet engines, heat pumps, refrigeration systems. And so that's actually all the fun that's now set up now that we've kind of gone through all the basics that we can kind of get into. So imagine, for kind of the first most basic cycle would be I have some sort of hot reservoir and I have some sort of cold reservoir, and there's some process in the middle. And that's usually how it's drawn in a textbook, some sort of process. And what I'm getting out of this is some sort of cycle work, okay? And the difference out of that cycle is going to be basically the difference between the amount of heat coming from the hot source and the heat that's leaving. So that would be just basically your basic energy balance, and that's what's happening. And so as a reminder, we would define efficiency as the thing you're wanting, which is, if this is an engine, I'm trying to get cycle work out of it, and then the thing I'm spending is actually the thing coming from the heat. Okay, and so if you do that kind of with a formula, you would see that this is just basically the ratio of heats. Okay, and so the most simple cycle is called a Carnot cycle. And ultimately, this cycle is very basic, and it's effectively what is shown here above. And that, imagine you have sort of a system right now that's insulated, and a piston, and it's coming down. And so this is pressurizing. So this is your compression stage. Okay, but we're going to compress with no heat leaving the system. And so this is going to be states 1 to 2. And then we would then open up the system and drive sort of the piston back up, but we're going to add heat in. So at this point, heat is going to come in, and that's our Q hot. And so this is heating. We'll call that 2 to 3. Okay. And then we're going to let this thing keep carrying on, and so it'll keep going up. At this point, it's expansion. We'll say that's 3 to 4. And then now this has sort of reached sort of regular pressure, and then we'll kind of push it back down. But this expansion is going to happen, again, I'll back here and say it's insulated. So we'll make sure no heat leaves the system after we put it in. And then as you drive the piston back, this is then heat going out, which is then going to be going to our cold sink. Okay? So this is rejection. Now, it may look funny, like how would you actually do a system like that? We'll come and show a few more examples of how that would really work. But in that process, this is the basic, the most basic thing you can do. And ultimately, if you look at sort of the two diagrams we're going to talk about, so TS and PV, right? Because the hot source and the cold source is all coming from basically one temperature, this is actually the easiest diagram to write. It's basically just a block, okay? And so when we compress, you actually do add heat, going from 1 to 2, right? You compress, you're going to add some heat, and then 2 to 3, that heat is coming in from a constant temperature source. And so constant temperature heat goes in, so entropy increases. And then expansion back down to sort of pressure 4, and then reject the heat. And so this is, again, this would be sort of, you might, in a diagram like this, talk about QH coming in, and then Q cold going out. On a PV diagram, well, it looks a little bit different, okay? Right, and I'll draw on here, this line, sort of the extended line here, is T cold, and the sort of extended line here is T hot. And so we're going to start at 1 and go to 2. That's a compression. So again, as I adding a pressure, this is pressure, I'm going from cold to hot. I will then add heat while staying cold hot. I will then expand back down to the original pressure I started with, but actually gets to be back down to TC, and then reject the heat by sort of bringing the volume back down. Okay, so this is Carnot. And also, if you go back to this efficiency and you do it, then you're going to see this is just TC over T hot in the end, right? Actually, because QC is just the temperature times the entropy. Well, you have the same width here, so the delta S is the same, and so this just reduces to that. So this is the most efficient cycle you can ever have. And so a lot of times you'll hear, well, what's the Carnot efficiency? Well, it's literally set by those maximum temperatures. And so nothing can be more efficient than that. Now, can we make a Carnot engine? Not really. And so all of sort of the real applications will be some sort of, reality is going to step in, we're going to have to do something slightly different. And so it'll be a little bit less efficient than this mythical Carnot cycle, but we can actually build it. Okay. So for example, one of the things we can build, we could actually come over here, and I'll draw it up like this. We can build, I'll use a sort of a vapor dome. And so if I have a system that's a vapor dome, those would be a PV diagram. Then, and this could be water, right? Water going to steam, or it could be honestly any kind of fluid. This would be T hot, this is T cold. And so when you're sort of boiling water, if you will, if this is water, if you're boiling water, your temperature stays constant as you're sort of adding energy, and the pressure stays constant. And so you could actually build a cycle where you sort of compress and then reject heat. You could kind of build like that. You get kind of close, okay? A couple of the challenges there, right? If you actually tried to build this, a couple of challenges, and I'll sort of draw what this looks like, okay? So here would be a turbine. The turbine's going to drive a compressor. And so going this way, 1 to 2, this is your compression. And then here's where that Q heat's going to come in. So whatever you're burning inside of there, a boiler, you're burning coal or natural gas fired to sort of boil that water, and then you're going to drive across the turbine, okay? And then you're going to maybe cool down that water. Maybe this is with a lake or air, sort of external heat exchanger to kind of get back to the system. Now, a couple problems are going to occur with this, right? And so again, this is 1, 2, 3, 4. So if you're actually going to make this Carnot, the biggest problems actually happen right here. I want you to think about that. Let's look at the turbine first, going from 3 to 4. So this is starting with vapor, but as soon as I start going over my turbine, I'm picking up little bits of liquid, because this is where everything is liquid, this is where everything is a gas. And so if I do this right here, then I'm actually, my turbine is then having little bits of droplets of water slam into it. And so you can't build a system because that turbine just gets completely destroyed, okay? And then same thing over here. If I come over here, I'm now maybe 70% liquid and 20% gas. And so this is a very bubbly liquid and I'm going to go put that into a compressor, same sort of thing. Like that's just going to chew up the compressor. That really just kind of destroys it. And so, you know, the reality of the thing that you end up doing, and we'll cover this here in a little bit, but the system that you end up drawing looks a lot more like this. Okay? And I know this is PV, and so I'm probably going to screw this up. I usually draw in TS. Okay? And so what you would do is you would actually start your state 1 at liquid, such that your pump can go to state 2, such that your pump stays fully liquid. Okay? That's actually a lot more efficient. And then, yes, you would spend some amount of time, you know, heating your water, and then you would actually get past the point. In fact, this has to go up. This has to go up. All right, so there's 2's up here. You would then heat your water and get past that point, and you would actually go all the way to what they would call superheat, such that when you expand all the way across your turbine, you're actually still a vapor. And so this is what it would start looking like. But if you notice, this is no longer a square, especially if I start drawing on the TS diagram, which is how I'm much more familiar in drawing with them. This becomes not a square, and so it's a little bit more complicated, but more primarily, it's a little bit lower efficiency than this. But you can build the thing, okay? And so that's kind of the realities of what we start getting into. And so I'm going to wipe the screen here and come back a little bit and talk about entropy. Because again, I keep drawing these sort of PV diagrams. Again, what's nice about PV diagrams is, again, a reminder here, this area is work. The areas here is heat, but what we're going to start getting to more, we're really just kind of looking at TS diagrams. Because ultimately, when you talk about real systems, you actually are talking about inefficiencies that creep in. And so we need to start looking at things on the TS diagram so we can track those inefficiencies. And then if you wanted to go PV diagram, you could go work through it. Usually what people end up doing, you sort of draw the TS diagram. You can kind of solve all the pieces there in the TS diagram. You would draw sort of lines of constant pressure on the TS diagram so it's complete. And then you would just kind of work through and solve it. So I'm going to erase the screen. I'll be back in a second. Okay, welcome back. Screen's cleared. So I could do the last little bit here. Now see, it's kind of manipulation of entropy. And this is actually in chapter 6 portion of thermodynamics. But really, so we know that Q is equal to, well, I should say, the integral of TdS. And so you could actually change this around if you wanted to and say, well, what's my entropy change? If you could say delta S, it would be, I'll use a circle here, I'll talk about it, and it's a Q, all right, dQ over temperature. And what this one means, again, mathematicians usually are better than this. Engineers are pretty horrible. This, in this position, just means it's path dependent. And so it really depends how you get there. It's not so much just about the end states. Okay, and that's usually sort of good enough for now. But really, entropy is a thermodynamic variable, and so all of these entropy values or change in entropy values you can look up in tables. We've talked about RefProf or CoolProp within the computer, but there are a couple interesting ways you can actually calculate it, and that's kind of what we're going to finish with here. Okay, and so one of the ways, sort of the easiest version, if you will, and so you can say, if entropy is a function of pressure and temperature, and you're talking about a fluid, well, then actually the entropy of the fluid is really just going to be dependent on temperature, and that's true for almost any thermodynamic variable. The thermodynamic variable isn't going to depend too much on pressure. You got to be really careful. Again, I'll talk about my world and rocket engine experience. Those are at high pressures. Like you got to look up the variables. But a lot of times you may see in some problems that you're working through, sort of this might be that key assumption that's blocking you from solving the problem, or at least this is giving you a good estimation. So you gotta watch out for that. But the other one, if it is incompressible, which I know is normally fluids, incompressible, then you do have a couple other things you can do. So ds, and again, this is just rewriting the thermodynamic equation differently, is du over t, and then you got a plus p dv over t. That's just rewriting the thermodynamic equation. And so if we are then incompressible, and again, this is a change in specific volume, then I want you to note that, well, if this is incompressible, then there is no change in density, no change in the inverse density, specific volume. And so this just is this one. And then you might say, well, that's actually just the specific heat, CV, times whatever that change in temperature is over temperature. Okay, well, that's starting to look like a thing we can integrate. Okay? And so then it's just S2 minus S1 is that integral, CV dt over t. And if it so happens that, and it's not always true, so you could be careful, if it so happens that you have a constant specific heat, then that can actually get really easy. Then it's just CV natural log of T2 over T1. And so you can actually figure out the change in entropy if you have a constant specific heat and it's incompressible. So that's an easy one, right? Likewise, one that's also easy, which shouldn't be that big of a surprise, is ideal gas. Okay? And same sort of thing. We'll write here ds is equal to du over temperature plus p dv over temperature. Okay? But I'm also going to write the second line down here, which we can then, if we switched over to enthalpy, remember that by adding sort of PV to each side, then this is d enthalpy over temperature, right? And then plus, actually it's a minus. So that this is then a minus V dP over temperature. Okay, and so same sort of thing. If we expand that as well, and then you could say this is CV dt over T. Well, if it's ideal gas, I have P over T. Well, what is that? That's just R. Right? R over V. So then I have an R dV over V. And then same trick here. This is, if it's the CP, remember CP is associated with enthalpy. CP, d temperature over temperature. And then you'd have a minus, again, what's V over T? Well, that would be R dP over P. So, right, in the exact same vein, you can then come through and say that delta S, you can integrate both of those. Again, I'll skip past the one, just be careful that CV can be a function of time. Can be a function of temperature. And so you get CV natural log T2 over T1 plus R natural log V2 over V1. And in this case, you'd have CV CP natural log T2 over T1 minus R natural log of P2 over P1. And so if it's an ideal gas, right, you can actually get a lot of mileage out of these two relations. Okay, and then one of the fun things that we'll kind of finish on here on this episode, right, to sort of get into sort of the motivation of the things that you can start doing with this, and we're gonna motivate things here a little bit more. You can take a look at, say, a heat pipe. And so what is a heat pipe going to do? Okay, heat pipe very simple system. Okay, what a heat pipe is going to do from 1 to 2 is it's going to raise the pressure. And then this is a heat pipe. So this is your sort of in your house or indoor. Okay. And this is now hot. And so what's going to happen is heat. You're going to flow, basically flow air and heat exchange air with this hot refrigerant that's in it, and heat is going to flow from this really hot refrigerant into the air, and then heat your house. And then it's going to come over here, having given up some heat, and this is a throttling valve. And so we actually covered this before. And so throttling valve is going to mean that enthalpy 3 is equal to enthalpy 4. And then over here, this is now really, really, really cold. So you would then reject this to the outside world again. Okay? And so, kind of a heat exchanger. So, what this looks like then under thermodynamic diagram, and this is TS, like I mentioned, and I'm finally going to get to draw things in the TS diagram space. What this is going to look like is that this is your low pressure leg, okay? So I'm going to do dot dot dot, low pressure leg, and then you're gonna get this low pressure leg to where it's definitely, you know, you don't want to be pumping liquids, so you're going to make sure it's a little bit in that superheat regime, and then I'm going to draw a dotted line here that would represent sort of higher pressure. So this is P high, this is P low, but this would be ideal, completely ideal gas. So here's one, a perfectly isentropic pump, which doesn't happen. And so because entropy always increases, this pump, the realities of this pump is going to mean that my actual process is going to run to the right. It's going to go right. Entropy is going to increase. And then it will come along here. And in fact, I'm going to come along to the point here where I'm now clearly a fluid, so well into the fluid regime, because then what I want to do is then cross over through that entropy valve and be over here. So I may cross into the point where it's multi-phase. That might be okay. So depending on your system, you might tweak it. So that would be state 3, and here's 4. Okay, and so on this cycle, you're actually running around the diagram this way. And so you can actually, there's a good example of this in the book. You actually go through and calculate all of this. And the reason I'm drawing it is this is the first time you can really have real calculations. You can solve for how much heat am I putting into the house. Well, that would be the difference between enthalpies between state 2 and state 3. And let me rephrase. This is usually called state 2s, and this is state 2. 2s being if you had it done isentropically in state, and then state 2. And a lot of times in these problems, what you're going to be given is the efficiency of this mechanical device. And so in this case, the pump, an efficiency, you always need to make sure that efficiency is always less than 1, right? And so in this case, the H2 is going to be bigger than H2S. That's the easiest way to remember it. Okay, H2 is going to be bigger than H2S. So this would be H2 minus H1. And up here would be H2S minus H1. And so if you're given an efficiency, then the way you would solve this is you might have, say, the pressure and temperature. You have full knowledge at state 1, and then you're told what the pressure is, but you need one more piece of information. Well, in this case, the extra piece of information you have is that the entropy at state 2 is the same as entropy at state 1. So that's complete. So you can actually solve for state 2s. Now, through this efficiency, if they gave you efficiency, said it's an 88% efficiency pump, well, then you can solve this equation, and you can solve for H2. So now you have H2. And then, maybe they have to give you some sort of temperature over here or different conditions, right? This is sort of where you're sort of walking your way around the diagram and figuring out what do you know, what do you not know based on it. So, dear reader, this is where it's important for you to go, read the book, but do those examples. Again, there's tons of great examples. There's tons of great homework in each one of these books. I'm just hitting the wave tops here. I'm just giving you sort of the theory and the fundamental, sort of that theoretical minimum. But for you to truly kind of grasp and understand, you got to go do the work. You got to go look through examples. You got to go do some homework. And again, this is really going to set us up well. And I think where I'm going to head on, we have a few more lectures here to go on the thermofluids. I am going to get back into some of that graduate level as well, so you can really see the richness of thermofluids. But because where I want to head next on the next book club is I want to be able to get into rocket engines, and I want to be able to get into jet engines. Really, two great books in there. And so this sort of fundamental in thermofluids is going to be really, really good. So we'll see you on the next episode. Remember, if you are liking the book club videos, please like and subscribe. See ya.